Good morning, everybody. It's Paul Evans here from WasteMINZ. Hey, thank you very much for joining us for this morning's webinar, which is on leachate treatment basics with Simon Eldridge. Now, obviously, leachate management and treatment is increasingly becoming a really important aspect of landfill operation in New Zealand. And this webinar is really about providing a high-level overview of what needs to be considered when assessing the various options, as well as during the design and operation of a leachate treatment facility. So Simon will draw on both local and international experience to highlight some of the common pitfalls and really outline some of the lessons learned. And this webinar is actually based on a shorter presentation which was given by Simon at the 2015 WasteMINZ conference. So just a little bit of an intro for our speaker this morning. Simon is a business leader for waste and a business leader for industrial for Tonkin & Taylor. She has over 25 years experience in planning, design and construction of civil and environmental projects, and that's in the UK, Africa, Middle East, Asia, Australia and New Zealand. So she's probably got plenty of frequent flyer miles there. She joined Tonkin & Taylor in 2005, having spent 6 years in England and then 9 years in Hong Kong, where the last 7 years she was the landfill engineering manager for an international solid waste contractor. And Simon's recognised an expert in waste minimisation options, landfill design, leachate management and treatment, risk management, landfill gas management and landfill closure and capping design. So just to quickly run you through the process for the webinar. So we've got around 20 of you on the line at the moment. We're expecting at least another 10 to dial in, but it's always the last minute Kiwi way. So if everyone talked at once, it would be a wee bit of chaos. So we've got you all muted at the moment. For ease, we'll save questions until the end of the webinar. So if you want to ask questions at that point, you just click the little raise your hand button on your GoToWebinar screen. Click on that, it notifies us that you've got your hand raised. And then when it's your turn, I'll introduce you, unmute you, and you can ask your question. And just so everyone knows, we are recording the webinar, and we'll be making this available on our website. So that's enough from me. I'd like to thank Simon and Tonkin & Taylor for making today's presentation possible, and I'll now put you in her capable hands.
Thanks, Paul. Good morning, everyone. I just, as Paul said, I'd like to run through some of the experience that I've managed to gain over the years through involvement in a number of different leachate treatment plants. A lot of what I'm going to talk about is based on overseas experience rather than a lot of the stuff that I've also been doing in New Zealand, but I'm happy to afterwards answer some questions and hopefully make sure that the examples I'm giving do relate to New Zealand, but it's always easier to use overseas examples sometimes so that people don't feel that their site's been particularly targeted in a presentation. So I guess the first thing to really talk about is the history of leachate, sort of the history that's really changed why leachate treatment's become more of an issue. So originally we had effectively tips on wasteland or in pits that those sites were typically not lined, and therefore there was no real need for leachate collection because leachate effectively would run out the bottom, and depending on the site conditions of the surrounding geology, there may be some effective treatment, or you'd end up with leachate plumes heading off site or potentially into contaminating waterways. With the increasing environmental awareness, we have introduced liners into our landfills these days, although there are still a lot of closed landfill sites that don't have liners. But there's an increasing number of landfills with liners, and then there's no need for leachate collection. With better landfill practices, we've been able to reduce the amount of surface water and groundwater infiltration that's going into the waste. This is a positive thing in the sense of generating less leachate, so in terms of leachate, less leachate, but that also tends to be that you end up with stronger leachate. And also there's potentially a little bit longer of a tail of when you are there is contamination. So nobody, I think, would question that leachate needs to be managed appropriately, and that management has changed, requirement has changed with time. So the future, I think that it's fair enough to say that we're looking at more larger, more remote landfills. There's increasing transportation costs, increasing regulatory controls, and also increasing environmental protection requirements as we get better at looking after our environment. But in parallel with that is that there's also an increasing pressure on municipal wastewater treatment plants. So the solution of discharging leachate to the local sewer may also become more of a difficult thing to do, as the municipal wastewater treatment plants themselves got increasing load associated with urban development. So therefore need to consider site-based leachate treatment and disposal. Just wanted to run a little bit through with how that treatment process, design process may actually occur. So the fundamentals are to understand what it is that the leachate is that you need to treat. I sort of think of landfills as being a little bit like a recipe, where you're never quite sure, you don't always follow a recipe exactly, and it depends what you put into a landfill will determine what you get out of it. But also the combination of different wastes will create different chemical reactions and behaviour within the landfill, create different temperatures, and therefore the leachate characteristics are quite site-specific based on the waste that you're taking in. There also needs to be the ability, you need to establish what treatment you're trying to get out of your treatment. So depending on where your final discharge disposal method is, your treatment objectives may be different. So you may be looking just to get rid of colour, you may be looking to get rid of ammonia. There's all sorts of different aspects that you might be looking at, and it is impacted on the disposal method that you choose. Therefore, it's quite important to undertake an initial options study, and out of that initial option study you can select the preferred treatment method. But desktop is all very well and good, but we all know that the importance of understanding your own individual sites, or particularly with some of the historic sites where you don't know very much about the waste itself. So therefore, even if you've chosen a treatment method that seems to be a good idea, it's really important to carry out pilot trials to establish what might need to happen going forward. Then you get to the point where you can, when the rubber hits the road, and you can design and construct your plant. But it doesn't really stop at that point, because after that there is the need to tweak or optimise the operation of that plant. So I'm going to take through some examples, take through those stages, and then at the end, Paul's going to keep me to time to make sure that I don't run out of time to talk about the actual examples. I'm going to take through some examples where some of these aspects are discussed in a little bit more detail. So those of you who know that I also talk about landfill gas, this figure is quite similar to the landfill gas generation figure, but effectively what it shows is that the composition of leachate changes with time as the degradation process proceeds, and therefore the contaminants that you're trying to deal with can change quite significantly over time as well, and therefore the flexibility is in a treatment process is quite important to be able to understand this. So what did that really mean? Well, leachate quality, in reality, it depends on the nature and the age of the waste. So it's quite important to know where you're at in that degradation process and where you're likely to be going to. And as I said, that can be a real challenge on some of our historic sites. So therefore it's important to characterise that leachate quality and then get a feel for what that might mean on the cycle. So in the early stages, leachate is referred to as acetogenic. Generally that's your high waste, your young waste, and it's characterised by high COD, carbon oxygen demand, high BOD, and then the ratio between your BOD and your COD also appears to be high. Now that leads to some challenges in that your treatment plant may have you may have sort of low flows, but very high in the early stages of the facility, but really high contaminants to deal with. The other thing that tends to occur with acetylogenic leachate is scaling issues. So your pipes quite often can get clogged, or even your drainage media, and therefore the importance of making sure that your collection system can be cleaned out. But at the treatment side, if you're using pumps or diffusers or any mechanical equipment that has like small holes or impellers, then you can end up with problems with scaling. And it's very hard, the carbonates are very hard, so they're quite difficult to take off and can result in quite a lot of wear and tear on your equipment. As the waste degrades, and the older waste that goes to the methanogenic phase. So methanogenic, that's when you're getting your landfill gas as well. So you've got other issues that you're dealing with, but it's also the leachate changes, and in reality the leachate becomes a much easier, the quality is easier to treat. So it tends to have a lower COD, and it also has a much lower BOD, and there's a lower ratio of BOD-COD. So taking leachate samples of your leachate and characterising it helps assess where you might be on the degradation process. The type of treatment and the efficiency of that treatment is impacted by the phases that you are on the degradation cycle. I'm not sure. So HELP is a model that was developed by the US EPA. It's a hydrological model for evaluating the quantity of leachate that you might get from waste. It is a very useful tool, but as with all models, it is based on assumptions, and unless you can verify those assumptions, it only gets you so far. So the inputs to HELP relate to the type of layers that you've got through your landfill profile, whether you've got a cap on or place, the depth of the waste, and then what happens down and how your drainage system might work at the bottom. You apply rainfall data, you apply evapotranspiration data, and all of that, and it goes into a nice black box of analysis, and it spits out answers that experience shows can really be a good indicator, but not true necessarily reflect what your quantity is going to be. So I'm a huge advocate of detailed site-specific water balance modelling, and then taking time to statistically correlate that against actual flow data. Now, when we get to the examples, I'll give you an example of how that, what that might do, and how that might become quite important. There's also, depending on what you're doing with your what's happening with stormwater, whether you've got a lot of groundwater infiltration, so depending on whether it's a lined or an unlined site, depending on the diversion of that stormwater and whether you've got bypassing, it's really important in a leachate treatment perspective to understand not just the average leachate generation, but also your peaks. So how long are the peaks? How frequent are those peaks? Do you live in a climate where you're likely to get multiple events? Because all of that needs to go into an assessment around how big your plant needs to be and how much on-site storage you need to have to balance those flows. So if you've got a lot of surface water infiltration or groundwater infiltration, that might be good in the sense that you've got good dilution of your leachate and it might be easier to treat, but your plant can only physically take a certain amount of flow through it. So the treatment facility will be limited not just by the level of the contaminants, but by the physical quantity of flow. The landfill phasing and how you operate a site has quite a lot of impact on leachate quantity as well. So that's about same sorts of things about whether you can divert surface water and how you are managing runoff and various other aspects. And then one of the things that's quite important is around flexibility, is that looking at quantity may lead to a phased installation of a treatment option. Final disposal options. As I suggested, it's very important to know where your final disposal option is when coming up with the best solution. You may still discharge to a municipal or a community sewage system once you've maybe dropped the ammonia levels down to an acceptable level or changed any other parameters that that particular plant is concerned about. There's an opportunity potentially to discharge to land by either spray irrigation or subsurface irrigation. The ability to recirculate back into the landfill. The discharge to natural water, the photograph on the screen there is of a reed bed to enable leachate that's been treated to be finally polished so that it can be discharged to forest just in the background of that photograph. It's in Malaysia. And then other options is that it may be used for, you may choose to evaporate the leachate, and that using heat generated from the combustion of landfill gas, so if you've already got a landfill gas system in place, or actually using the landfill gas itself to create that evaporation temperatures. The treatment options, as I suggested, is very much based on, you need to look at your treatment objectives, and from your treatment objectives there is the ability to ascertain what your main treatment options might be. I'm not proposing to go through all of those at this point. They are a little small on your screen. I guess there's an advantage that you can get close to it. But those various, that's sort of a good sort of rule of thumb around what type of treatment options may be appropriate for specific treatment objectives. So I talked about trials and the importance of doing pilot trials to test whether the treatment option that you are proposing is one that will be viable for your specific leachate. The field-based trial plants are certainly important when it comes to biological treatment options, and I also believe that they're really important for some of these more sophisticated treatment processes that are being proposed by international suppliers. And I think there's a real challenge there, because the suppliers don't necessarily want to go through the expense of bringing their kit to site, but yet as the purchaser of that equipment, you need to be pretty sure that your leachate is going to be treated to a successful level based on the treatment option that you're choosing. So we use pilot trials to test design assumptions. The hydraulic throughput is particularly important because, as I said, that's a combination of the readiness of that leachate to be treated, the influent quality, and how that it behaves within the treatment that you're choosing. One particular situation I had related to a relatively early reverse osmosis plant, and what was found is that the hydraulic throughput for the particular leachate, it was a closed site for the particular leachate that was being proposed, because of its own individual composition, was significantly less than the supplier had expected. And so a whole lot of changes needed to be made to try and get that plant to have the hydraulic throughput that was assumed at the desktop stage. The chemical requirements, so depending on the quality, you may need to add chemicals or chemical addition to get the treatment plant to operate efficiently. And then also I think it's important to understand the flexibility of the treatment process. So if you do have significant storm events, so you end up with a dilute leachate going through, and then once the storm event passes you end up with a plug of quite a strong leachate, or you're opening up a new phase, it is quite important in the trial process to see how robust the treatment process is. The reason why I recommend it being field-based at the site is that you also need to reflect on the variety of operating conditions you may get at your site, so ambient temperature and the range that you might accept, and then, as I said, said before, the quantity and quality fluctuations are also really important. So once you've chosen the treatment plant and you've managed to demonstrate that it will meet the requirements or what you choose, then there are a number of different ways that you can procure the treatment processes that you want to install. Now, depending on the complexity of the treatment option that's being proposed, probably has a significant impact on which procurement option you may choose. So a prescriptive design, something that's relatively straightforward, that you're very confident that you can specify down to the last bit. So then you might choose to use a traditional construction contract, that we may use on a road or on other parts of the landfill construction or closure. You'd have a specific design phase, then you would go into a construction phase, and then an operation phase. However, the more complex that your process gets, and also the more proprietary that the process might be, so you might choose a particular treatment method that is specific to a supplier, then a performance-based design may be a little bit more important. So you would do your concept design, and then you do design and construct, and a handover for that to be operated. But it also might be so complex, or it might be that as an individual entity you don't have in-house ability to be able to operate that plant. So you may choose to do design, construct and operate. The other thing that as I was talking about with the challenges that sometimes we have in relation to getting suppliers to provide what we need for trials. I mean, some basic biological trials you can do yourself with technical support, but if it's a more complex treatment system, then it might be that you need to get the supplier involved early, and that's in that early contractor involvement type space, and that can either be a prescriptive, sorry about the typo, or a performance-based design. More often than not, it's likely to be a performance-based design. So the challenge really is decide at what part of the process does the do you start with your combined approach start? So before or after the proof of concept. And I guess the main thing there really lies on the impact of your risk allocation and the ability to embrace innovation. So if you don't get your supplier involved until quite late in the piece, and you've already fixed what it is that you want to do, you may have some struggle with getting some innovation into the process. But equally, you may end up with issues in around who's really carrying the risk on the plant operating effectively. Something that often gets forgotten in this process is we get enthused and excited about the construction process, and the commissioning aspect of a leachate treatment plant is equally as important. I was talking to a client recently, and they were saying, well, one of the things that always frustrates them when they get water treatment plants is that it takes them forever to get the O&M manuals, and if they've gone through the commissioning stage and they're already trying to operate it, then the O&M manuals are really important. So having all of that information up front is also really important. And commissioning always seems to take longer than you think. And I am going to get on to some examples which will highlight that. Now, I think it's really important that that the commissioning you engage that everybody gets engaged in that process and is working together. Don't leave, rather than leaving the supplier to do the commissioning and say, here you go, it's all working. It's quite important to have your staff involved, particularly if they're the ones that are going to be operating the plant. But even if they're not the ones that are going to be operating the plant, it's important to see the process that the supplier goes through for commissioning, because it can often give you some insight into what happens going forward. And then, as I said, because the leachate quality and quantity changes over time, and because it's often impacted by ambient conditions, there's also a need as you go forward to optimise operations as things change. So I'd now like to take you through some examples of projects that I've been involved in, and some of the lessons that I've learnt over the years. So this is a large treatment facility in Malaysia. The requirement by the Malaysian government was that the leachate would be treated to a level where it could be discharged and cause no problem to the natural waterways around the area. So the intent was, as I said, I showed you the photos before, if it goes through a reed bed and then it gets spray irrigated to forestry land. The level of discharge is to a level where it could have gone straight into a stream, was the requirement. So unlike some spray irrigation which we allow in different jurisdictions where you can still have, allow for high ammonia contents, this was not one of those cases. So the plant was built at the same time as an advanced cell was developed for the landfill. The plant was done based on laboratory testing rather than necessarily site-based pilot trials because of timing. When I got involved in this particular project, the site was up and running, but it just wasn't treating the leachate at the level that it needed to be treated. And there were a large number of storage ponds littered around the site with the leachate being stored while all of this was trying to be sorted out. Now, the main thing I think that probably also influenced on this site is that partway through the development of the advanced cell, the government was convinced by some external parties that they needed to run the advanced cell as a semi-aerobic landfill. And that involved allowing a lot of water to pass into the landfill, but also the aerobic conditions associated with allowing air to be drawn into the landfill. That completely changed the leachate quality, and also being Malaysia and high rainfall, there was also an awful lot of lot more leachate being generated than was required. So it was really a little bit like a perfect storm. There was no doubt why this leachate treatment plant was designed by a person with a lot of leachate treatment expertise, and yet the plant just didn't work. When I got involved, there were a couple of things that we did. First of all, we brought in another expert who had some really good experience. I'd worked with him in Hong Kong, had some really good experience in dealing with optimising plants in tropical environments and some of the challenges associated with temperature changes and leachate quantity. But the other thing that the work in particular that I did was I re-looked at the leachate generation estimates to see what was going to happen with time, and then gave some recommendations around operational practices to reduce leachate generation. The exciting thing is that combination of getting in someone who was really good at troubleshooting, he managed to get down the chemical addition that was required for the biological treatment. He managed to get the system operating a lot more efficiently by adjusting this is an SBR system, so there's aeration, it's batch fed aeration, settling, then decanting. He was able to reduce significantly the amount of chemical addition, which was going to be quite expensive. And then with the changes in operational practices, the leachate treatment plant became an adequately sized, and they have, last time I heard, managed to get rid of a lot of the backlog of leachate, even though the site has expanded quite significantly. So this was an example of the sizing wasn't quite right, predominantly due to operational practices. The leachate quality that came to the treatment plant wasn't anything close to what was expected, but with the right optimisation around operations, it was able to adapt the system to operate efficiently. This is another site in Asia. This is in Hong Kong. This is also a site that really struggled with high leachate generation. This is the landfill footprint is 60 hectares, and those big black blobs are leachate storage ponds with a significant backlog, obviously, of leachate. Now, this site it was also designed, the treatment plant had to be up and running before the leachate started to be generated, and effectively in cetogenic conditions. A traditional approach was taken of a biological treatment process. However, it very quickly became apparent that the biological process wasn't able to deal with the ammonia. This is a zoom in on that biological process. So this is a downstream storage lagoon. There are to bottom, as you go down the screen, there's aeration and various other storage tanks. Now, this plant ended up optimising landfill gas at the site to strip the ammonia out. So that's an ammonia stripper or a smart flare, and that got the ammonia down to a level where it was then able to be treated in the rest of the plant. So the capacity of the plant was doubled just purely by putting in something that dealt with the high ammonia quality. Another site in Hong Kong, similar sort of challenges with generation. This site elected to put in vertical tanks to save space. So these the tanks that you can see there were designed to be all that they would need for their biological treatment. It was found pretty quickly that the aeration depth was really too high for the quality. Yet again, government required this plant to be put in before there was sufficient leachate quality, so no pilot trials were able to be done. The plant got to a point where once the site had been developed to a sufficient point, it just couldn't deal with the treatment. It was fine to begin with, but it needed some additional treatment capacity. The solution for this site also related to putting in a smart flare, an ammonia stripper. You can see that on the right-hand side of the screen, and just behind it is the tanks that were originally the biological treatment tanks. They became storage tanks, and new biological treatment tanks were built on the side of the landfill, which you can see in the photograph on the left. And they are much shallower. They have a significant amount of surface aeration in them, which enabled the treatment to take place in a more efficient way, and then they are pumped back to the treatment plant prior to discharge to sewer. So I guess the last two sites that I've shown you are a good example, or the three sites are really good examples of different solutions being able to be adopted to improve the capacity, but all of these sites were developed before there was an ability to put in pilot plants, and therefore they needed quite a lot of optimisation. This is a closed site. It's also in Hong Kong. The depth of waste is 140 metres. These are 1-on-3 slopes. They would have been fantastic ski slopes if we didn't have to put surface water control all the way down the front face. At the toe of the site, a leachate treatment plant has been built. This site had a couple of interesting challenges in the sense that the leachate treatment plant itself was able to treat the leachate, but groundwater intrusion, it's an unlined site, groundwater intrusion from the surrounding land area was a lot more significant than was anticipated, which was a positive thing in one respect, in the sense that the treatment plant was able to cope with quite a dilute leachate. But on a downside, the quantity, particularly during the rainy season, was so significant that it was apparent that something needed to be done. So at this site, to reduce the treatment costs, a groundwater interception bores were subsequently constructed to intercept the groundwater before it entered the waste mess, so that it would reduce the amount of leachate that needed to be treated, and therefore able to be treated in the plant. So this is a photo of this too has a smart flare, but it also has other landfill gas flares for treating the landfill gas from the site. If anybody's going to Hong Kong, when you come in on the airport railway cuts through the middle of the site. So it's quite an interesting site to be seen from the train if you're interested in it. It looks like a really nice sort of greened area. So I guess just some closing thoughts, perhaps a bit fast, but hopefully there might be some time. We have time for some questions. I guess the overarching things for me is that really it's very important to understand your specific site conditions, whether it's a closed site which you know a lot about, or an active site, a closed site where you don't necessarily know about it, or an active site. You really need to do your absolute must is to try and get as much site-specific information that you can possibly collect over a period of time. Then it's important to understand what's likely to change over the treatment, the life of the treatment plant. So what's likely to change with respect to the leachate quality, the quantity, and then discharge constraints. So you may develop a plant and get acceptance to discharge to the local sewer, but you know, with increasing, as I've said about increasing pressure on our municipal treatment wastewater treatment plants, perhaps at some point in the future you may find that it becomes either prohibitively expensive or you just don't get the ability to discharge to the local sewer. The other thing is probably a really good understanding of leachate generation estimates. The quantity and the frequency of peaks and how you're going to deal with those peaks is extremely important in sizing a plant. The site that the steep site that I referred to, which was the slide before the last one, that site, you know, really, to be honest, the amount of groundwater intrusion and the impact that had was underestimated at the time of sizing the plant, and it was therefore the only real economic solution was to intercept that groundwater and reduce the size of those peaks, or the size of that treatment plant would have been too significant. Then do you have the capacity for storage on site, and what those storage requirements might be, and then what their likely impact is on quality. I mean, dilution is a great thing, but it can also create challenges in if you've got cyclic dilution with climate impacts. I've talked about the importance with pilot trials. I have highlighted some sites where that was possible and sites where it wasn't possible, and what an impact that had. I've deliberately used big sites because they had significant impact, but can equally have an impact on the smaller sites. The other thing is that leachate treatment design is very different to municipal wastewater treatment design, and I've experienced this quite a lot, where designers often have rules of thumb, and I guess the aeration depth is one of those. Those rules of thumb don't necessarily translate across to leachate, and it's quite difficult sometimes for a wastewater engineer who's been designing things in a particular way to necessarily flip their brain across to understanding that with leachate it's different, and it is important that that people understand that difference. I'm a big advocate of performance-based specifications. I think that we get our best stuff by going to the specialists in fields and providing them with the framework with which they need to deliver, and then obviously that needs to be demonstrated, which is another reinforcement for the PIA trials. And then the other aspect is the ongoing operational optimisation. You can improve the efficiency of your treatment plant, and as with all of the things in waste, nothing stays the same, so it's important to deal with that as we go. So I'm hoping that that was a reasonable introduction to leachate treatment basics, and I'd be happy to answer any questions.
Cool, fantastic. Thank you, Simon. Now, just to run through the process again, if you do have any questions, you just click the raise your hand button on your GoToWebinar screen, and then we can unmute you and go from there. I've got a couple of questions, Simon, just to kind of lead off. You talked in there about composition changing with time, composition of the leachate. So how do you deal with that? How do you manage it?
So there's a couple of things that that can really work with treatment facilities. The composition changes with time means that sometimes a modular approach to a leachate treatment plant is a good idea. So you can start off with something and change it as you carry on, as you go through. The other thing is to make sure that you don't have a highly strung leachate treatment plant, so one that's quite flexible and deals with changes in composition and doesn't spin out. There's a few modern processes that are very good for a consistent composition, but they don't necessarily cope particularly well with variability.
Cool. And in terms of, obviously you talked about on-site treatment options and off-site options, so I guess at what point do you really need to start thinking about those off-site ones?
As a site tends to start consuming space, sometimes you can start running into limitations on space necessarily for maybe spray irrigation or some large lagoons where you might be getting some good evaporation. The other thing I guess is that the need to, but the simplest solution is always going to be dumping into a sewer. So keeping a handle on what your local municipality may be doing with their treatment plant and whether that's going to be a long-term solution for you, or tankering, might be that you're tankering it rather than putting it into a pipe. But keeping an eye out about what might be changing in your environment is also really important.
Yeah. And in terms from me, you obviously talked about the importance of pilot trials to test that things actually work as you think they're going to. How long do you need to run those to get, I guess, get a good understanding?
That's a good how long is a piece of string question, and it depends a little bit on the process. A minimum time for a pilot trial generally would be about 3 months, which I know sounds like quite a long time, but you need to get as much variability into the pilot trial as you can. But the other thing is, particularly for some of the biological pilot trials, is that you need to give the system a chance to settle down as well as being able to give it some variability. So that just all takes time. So it can be that you need, you might even need 6 months to run a pilot, which is a significant cost, but at the same time, it's going to give you the best answer. So the long and the short of it is, the longer you can run a pilot, the more reliable the data is that you're going to get out of it.
Fantastic. So that's it from me. Does anybody on the other end of the line have any questions? You speak now or forever hold your peace. This is your opportunity to ask those, so just click on that raise your hand button. If it doesn't appear we have any coming through at the moment, so you've obviously answered everything with 100% accuracy that no one can disagree with, Simon. I'm sure you'll like that. Cool. Hey, fantastic. Thank you very much, everybody, for joining us today for this webinar. It's been a good turnout there, and I'd like to thank Simon and Tonkin and Taylor for making today's presentation possible. So thanks very much, and have a fantastic day. Cheers.